We're doing 21.3 combinations and probability. My wife here is going to help us. So we'll just jump into it. So a combination is similar to a permutation, except order doesn't matter. So for example, if I'm selecting from these four items, A, B, C, and D, I could select ABC, ABD, ACD, or BCD. Notice here that they're just in alphabetical order. I don't have ABC and ACB and BCA and all those other ones that we figured out before. The order here is irrelevant. What matters is that it's those three items. So let's jump into this example. A restaurant has 8 different appetizers on the menu, as shown on the table. They also offer an appetizer sampler, which contains any 3 of the appetizers served on a single plate. So how many different appetizer samplers can be created? So here we can choose, say, nacho chicken wing egg roll or nacho chicken wing quesadilla. But if we choose quesadilla nacho chicken wing, that's no different, right? We're still going to get, the waiter's still going to bring out our 3 items. It doesn't matter what order we choose them in. So let's figure this out, and we'll do it using our permutation information. So the first step is to find the number of appetizer samplers that are possible if the order does matter, right? So we're going to choose 3 of these 8, or 8 choose 3 permutations. So in that case, it's 8 factorial over 8 minus 3 factorial, or 8 factorial over 5 factorial, which is, that's why she's the calculator.
I don't know why I have the calculator. Divided by 5.
Which gives us a grand total of 336. Good job, you got it.
Is that right?
Yes. You just say it. You're about to do another one here. So there's 336 possible ways to choose 3 items, right? So this includes quesadilla, nacho, chicken wing, and chicken wing, nacho, quesadilla, as well as all the other possible 3 food combos as well. So we want to eliminate all of the repeat ones, right? So if I choose nacho, quesadilla, chicken wing, and nacho, chicken wing, quesadilla, and et cetera, et cetera, et cetera, just with those 3, how many possible ways are there to order those 3 items? And we've done this before. This is 3 choose 3 permutations, or 3 factorial, which is?
6.
Yes, very good, 6. So we simply need to divide out these 6 possible options. So we're going to take 336 and divide it by 6. Note here we're not doing a what is a probability type thing. We just need the number of possible combinations we can do here. So we take our 336, we divide it by 6, and we get?
56.
Cool.
I did that.
Yep. So this brings us to this general rule here, where the number of combinations of n objects taken r at a time, so again this is n choose r combinations, is equal to n factorial over n minus r factorial, and we have to divide out r factorial. So this is our rule. It's pretty similar to the permutation one, but just keep in mind that we have to add in this r factorial, and that'll reduce the number a lot, actually, as it turns out. Let's do some examples. There are 4 boys and 8 girls on the debate team. The coach randomly chooses 3 of the students to participate in a competition. Let's pause right there. First, we want to figure out what the total sample space is, right? So what are all the combinations that the coach could ever possibly choose? Well, how many students are on the debate team?
12.
12. Okay, so there's 12 is our n, so it's 12 choose, and how many are we choosing?
3 of them.
3 of them. So that gives us 12 factorial over 9 factorial and 3 factorial, right? We're just following this here. 12 factorial over, what's 12 minus 3? It's 9. 9 factorial and 3 factorial. Which, when you plug into a calculator, it spits out 220. Okay, and then we read about event A. It says, what is the probability that the coach chooses all girls? So event A is choosing all girls. So how many elements are in the sample space for A? Well, how many of these 12 students are girls?
8.
8. And how many of them are we choosing?
3.
We're choosing 3, so it's 8, choose 3 combinations, which gives us 8 factorial over 5 factorial and 3 factorial, a grand total of 56. So in this case, we want a probability. This total sample space is going to be our denominator. The probability of, or the number of elements in event A is going to be our numerator, so it's simply 56 out of 220. And to be honest, I'll be totally happy with that. You can leave it at that. If you want to punch it in to the calculator, hint, hint, wink, wink, and give me a decimal answer, I'd be happy with that as well.
0.2545545454545, etc.
Maybe we should just round to something.
It's a quarter.
No. It's approximately equal to. So I'd be happy with you rounding to like hundredths or thousands or whatever. Just don't do like, oh, it's 0.3. It's not close at all. So give me a few digits to work with, so I'm convinced that you actually did the calculation yourself. And yeah, either one is totally fine though. So this would be 25.5%. You could put that down. That's pretty good. Something like that. Okay, let's try this one. Deck of cards. There are 52 cards in a deck, blah, blah, blah. 5 cards are randomly drawn from the deck. Okay, so we'll stop there. How many possible 5-card hands are there? This is your classic 5-card draw in poker or something. Does the order matter? What order I draw those cards in? No. As soon as I get one in my hand, I'm allowed to shuffle them around and switch them up. So the order doesn't matter. So we're dealing with combinations here, not permutations. The sample space consists of combinations of how many cards? 5, drawn from 52 cards. So our n is what?
5.
R is 5. Good. What is n?
Oh, 52?
Yeah. So it's 52, choose 5. So we're choosing 5 out of the 52, which gives us 5 factorial, or 52 factorial over No, we don't want 52 factorial.
Don't?
What goes in here? It says n minus r. What's n minus r?
It'd be
52 minus 5, which
5.
is?
Which is, get nervous.
Not a math major.
47.
Yep, 47. And then also r. We need r factorial as well.
Which is 5.
5 factorial. Yep. So 52 factorial over 5 factorial over 47 factorial, which, again, let's practice punching these into a calculator.
Punching in.
Just so we can get in the habit. I have no idea how I did that.
Oh, it's crooked.
I know. I don't know why. This thing. Oh, I gave away all the answers. You didn't see it.
I didn't. I wish I'd had.
Okay, hurry up. 52 factorial divided by 5 factorial divided by 47 factorial. And remember, what's cool about this is the 52 factorial and the 47 factorial, they kind of cancel each other out. We can cancel out this 47 if we change this 52 factorial to 52 times 51 times 50 times 49 times 48. If that's easier for you to do, 52 times 51 times 50 times 49 times 48, you can punch that in, and then you won't have these like stack overflow problems that the calculators might give you. Can it give you 51 factorial? Or 52
didn't
factorial?
Like that. No.
Yeah, it'll give you an error because it's just so mind-bogglingly big. It's like, yeah, it just blows my little calculator mind. The you know how it gives like error of how many digits, like how many zeros to put on there? It basically means that there are too many zeros to even write how many zeros there would be, right? It's like millions of billions of zeros or whatever.
Is that what the E meant?
Yeah. Did it give an E?
I got an E.
Oh, that's fine. You can do that. Yeah, that's fine. Do that one. What's 52 factorial?
52 factorial.
Yeah, there's 67 zeros. That's not a big issue. Okay, that one's doable.
Looks big.
And then divide it by something.
Divided by
47 factorial. So write 47.
7.
And then hit the factorial button.
Factorial.
And then hit equals.
Equals.
Cool. So we're back down into the billions. Or millions even. And then divide that by 5 factorial.
Okay, and then divided by 5 factorial is...
What'd you get?
2,598,960.
Yay, you got it right. Well done.
Thank you for telling me.
Okay. So this is doable with most calculators. And later on, I might even show you a shortcut. Event A consists of combinations of 5 cards drawn from, so in this case,
13.
we want to narrow it down. So it says, what is the probability that all 5 cards, that we're going to draw 5 cards. This is all possible, this one here is all possible 5-card hands. And then we want to narrow it down to which of these 5-card hands contain all diamonds. Well, there's a bunch of them that contain all diamonds. How many diamonds are there?
13.
Yep, and we're going to choose how many of them?
5.
5, so that gives us 13 factorial over
13 minus 5. 8.
Yep, good job. 8 factorial and
I get nervous.
and
5 factorial.
yes. Okay. So what's that come out to? Calculate
Okay.
quick. Go.
13
Kids are waiting.
factorial divided by 5 factorial equals divided by 8 factorial is 1,287.
Yes. Good job. Okay. So we know that of these 2.5 million or so possible poker hands, 1,287 of them are all diamonds. So the probability of getting all diamonds is simply the 1,287 out of 2.598 million, which is, again, I don't care much about this reducing a fraction, Jazz. I could care less that you know how to reduce fractions in this circumstance.
5, 9, 8, 6, 0. Very small.
Yeah. What'd you get?
0.000495198198079232.
So a tiny value there. Another way we can reduce it.
Should be a 2 because the 9 would round to a 2.
This is correct, but I erased it, so it's
Mr.
not an issue
Marcotte?
anymore. Another way we could do this is, a lot of times it like to do odds, is 1 out of how many. And so the way we could do that is we could divide both the numerator and the denominator by 1287. So what is 2,598,960 divided by 1287? And this time we'll come out with a decimal, but we'll round it. So this will give us just a kind of a general idea of the odds. What'd you get?
I got 2019 and some change.
Okay, so 1 to 2019 is your odds. So basically, every 2019 hands, on average, you'll get a diamond flush hand. So this kind of helps you figure out how likely it is, more so than a tiny decimal or a crazy fraction like that. It's just easier for a lot of folks to understand. I don't prefer these. Don't put your answers in this. But when we talk about poker hands, this sort of thing comes in really handy. And in fact, we'll do some problems where we work with that. Okay, see if you can do these two real quick. So pause here. All right, we'll just walk through it. Coin is tossed 4 times. What is the probability of getting exactly heads? These coin toss ones are a little weird because we can replace the coin, basically. We have a heads and a tails, a heads and a tails, a heads or a tails, heads or a tails. So this brings us back to our fundamental counting principle, where what is the probability of getting a head on the first flip?
50-50.
Yep. What is the probability of getting a head on the second flip?
Also 50-50.
Yeah, all the way down, right? There's 2 options here, 2 options here, 2 options here, 2 options here. So how many possible patterns could we get for heads and tail flipping for 4 flips? There's 2 here, 2 here, 2 here, 2 here.
So would that be not, wait. Would it be 4 factorial or would it just be
Keep going.
more additive than that?
Not additive, multiplicative. So 2 times 2 times 2 times 2.
Okay.
So that's 2 to the 4th or 16, right? So
Okay.
in this case, our sample space is that there are 16 possible patterns here. We could do heads, 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 heads. We could do heads, 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 tails. We could do heads, heads, tails, tails. We could do heads, heads, tails, heads, et cetera, all the way down until we got our 16 options. So this one asks, what is the probability of getting exactly 3 heads? Well, we could get, let's see, we could get our three heads as heads, 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 tails. We could get heads, heads, tails, heads, heads, tails, heads, heads, or tails, heads, heads, heads. And in fact, we can use choose notation to kind of choose um, which which three will be heads, right? So of these four, we need to choose three that are heads. So that is 4, choose 3, which comes out to what?
So that would be 4 factorial.
4 factorial over
3 and 1.
3 factorial and 1 factorial. Yep. Which, as it turns out, is just 4. Because the 1 factorial disappears, it's just 1. 4 factorial divided by 3 factorial. 4 factorial is 4 times 3 times 2 times 2 times 1. And 3 factorial is 3 times 2 times 1. So the only part that's left is the 4. So it's actually 4. Which gives us 4 out of 16, or 1/4. Cool. And there, done that. A standard deck of cards is divided in half, with the red cards, diamonds and hearts, separated from the black cards, spades and clubs. 4 cards are randomly drawn from the red half. Weird wording here. It just asks what is the probability. So we're drawing 4 cards here. So it's weird, 4-card hand, but that's fine. How many possible 4-card hands are there? And we're just drawing from the red half. So how many cards are in the red half?
26.
Yep, n equals 26, and we're drawing 4, so r equals 4. Yep, and that gives us 26, choose 4 combinations, right? Again, the order doesn't matter. Okay. I'm just giving you this one.
Thank you.
Let me off the hook. 14,950. Cool, so that gives us our total sample space, right? That's all possible 4-card hands of red cards. Now we need to narrow it down a little bit. It says, what is the probability that the 4 cards randomly drawn are all diamonds? Again, we want to get an all diamond hand with those 4 cards. This time we're drawing with, we're just talking about diamonds, n is equal to what?
Oh, me. 13.
13. And r is still equal to?
4.
4, yeah. So this is the number of elements in event A, which is 715. So 715 of these 14,000 hands, 15,000 hands, are going to be all diamonds, and then we can just come up with our fraction here. 715 out of 14,950. Can you give me a decimal on that, please, dear?
Yeah.
Again, you can reduce it if you want, but it's just as meaningless as having a giant fraction anyway. And it's just a huge headache to try and find how to reduce these, because there's a zillion factors in each one since they're born of factorials. So it's approximately equal to
0.048.
So I'm going to put 4.78%. 4.78%. Again, you can put as a decimal rather than a percent, but instead of putting 0.04 as a decimal, at least this is a whole value for a percent. So that's one of the reasons why we use percents, is so it sounds bigger. It's a little bit easier to intuit, 4.7 as opposed to 0.047 when it comes to something. So yeah, you can leave it as a percent. You can, again, do decimals. However you want to do it is fine. I'll accept all of them, but you need to be able to identify all of them on a multiple choice test. Okay, we're going to pause it there. Thanks for watching.